Hello everyone, welcome back to our channel. In today's video, we are diving deep into two important atomic models that shaped the modern atomic theory: the Thomson's plum pudding model or the watermelon model and Rutherford's nuclear model. So let's begin. Let's go back to 1897 when J.J. Thomson discovered the electron. As we all know, J.J. Thomson discovered the electron through the world's most important experiment in the world of atomic physics, the cathode ray tube experiment in 1897. This led him to propose an atomic model in 1904, commonly known as the plum pudding model or the watermelon model. So, when J.J. Thomson discovered the electron using the cathode ray tube experiment, based on his discovery, he proposed an atomic model in 1904, which was known as the plum pudding model or the watermelon model. According to Thomson, an atom is a spherical structure with positively charged like watermelon. You can see in this picture that this is the atom. This whole pink part is the positive part and the electrons are embedded. The electrons are embedded within this sphere like seeds in the watermelon. This looks similar to this watermelon. This whole red part is the positive charge, and this, like as the seeds are embedded into the watermelon, in the same way the electrons are embedded into this atom. He also said that the positive charge neutralizes the negative charge of the electrons, making the atom electrically neutral. He also said that the positive charge of the atom neutralizes the negative charge of the electrons, which makes the atom electrically neutral. There were some serious limitations of this plum pudding or watermelon model. It could not explain the results of the later experiments such as the Rutherford's gold foil experiment, which we'll be discussing after this topic. And he also could not explain, as you know, about the electrostatic force. It is a force which exists between two unlike or like charges. In the same way, as you know, atom consists of the positive and the negative charges. He could not explain how the atom is stable because when electric charges are squeezed into a small volume, they are expected to repel each other. But in this case, they were not repelling as the atom was stable. So to replace this plum pudding model, Ernest Rutherford made a gold foil experiment, which we'll be discussing now. In 1911, Ernest Rutherford and his team conducted the gold foil experiment, which led to a new understanding of the atomic structure. What is a gold foil experiment? We'll discuss. It was an experiment made by Ernest Rutherford and his team in 1911. As you can see, this was the experimental setup for this gold foil experiment. There was a thin gold foil of 100 nanometer. It was a thin gold foil of 100 nanometer and this was the source of the alpha particle. These alpha particles means, as you know, helium consists of 2 electrons. If you ionize the helium atom by removing 2 electrons, then we get the helium nuclei or the He2 plus ions, which is also known as the alpha particle. When these strike on this gold foil, the alpha particles, most of the alpha particles would pass through the gold foil. Some were deflected at a smaller angle and 1 in 20,000 bounced back. So we'll see what did these mean. First we'll see the experimental setup. As I said, a thin sheet of gold foil were bombarded with alpha particles or the He2 plus nuclei. As I said, helium has 2 electrons. If you remove those 2 electrons, you get the helium nuclei, which is also known as the alpha particle. And this, as you can see, this is the screen which was put around this setup, and this was known as the fluorescent screen. The inner part of this screen was coated with zinc sulfide, through which when these alpha particles strike this screen, then we would see bright dots on this screen, which would indicate that alpha particles are striking on this point. Next, observations of this model. Most particles, 99.9 particles, passed straight through, which indicated that atoms are mostly empty. And some particles deflected at smaller angles. As you can see, some particles reflected at smaller angles. This is because, as you know, there is a nucleus in the atom. When these particles, particles which deflected at small angles, went beside the positive charge, they got deflected at a smaller angle. But when a very small fraction, about 1 in 20,000, bounced back, when some rays fell directly on the nucleus, they bounced back, and this number of bouncing back rays is so small, as this is 1 in 20,000, which is a very small number. This indicated that the central charge must be very dense and very small. Next, let's move on to the conclusions of the Rutherford's nuclear model. Most of the space inside the atom is empty. As we discussed, many of the particles went straight through, so he concluded that the most of the space in atom is empty. Very few alpha particles were deflected, indicating the positive charge of the atom occupies very little space at its center. The atom consists of dense, positively charged nucleus at the center. Almost all the mass of the atom is concentrated in the nucleus. Electrons orbit the nucleus at a distance. Most of the atom is an empty space. By this, he said that in an atom, there is a small nucleus at its center, which is positively charged, and electrons orbit around this nucleus from a distance. And he also said that the mass of the atom is mostly concentrated in the nucleus. Then let's discuss why this model failed, or what were its limitations. Electron instability problem. According to classical physics, if electrons revolve around the nucleus, they should continuously lose energy. Like if you run about 10 meters, 20 meters, 30 meters, gradually you will lose your energy. In the same way, the electrons, when they revolve around the nucleus, they should continuously lose energy and spiral into the nucleus. If they lose energy, they should stop revolving and they will gradually fall into the nucleus, which says that the atoms are unstable. But in reality, the atoms are stable. So he could not explain why is this happening. He also could not explain atomic spectra. Rutherford's model did not explain why the atom emits light at specific wavelengths, leading to the discovery of the quantized energy levels in the Bohr's model. We'll be discussing this Bohr's model in our next video, and I'll also explain you about the atomic spectrum in the next video. So thank you. If you like the content, share, like and subscribe. Thank you.